The fastest object humanity has ever built would still need 7,000 years to reach the nearest star. That star is Alpha Centauri, sitting just 4.37 light-years away, closer to us than any other stellar system in the galaxy. So why does closest in astronomy still mean unreachable in engineering? Alpha Centauri is 25 trillion miles from Earth. That distance is over 270,000 times the gap between our planet and the Sun. If you place the Sun as a grapefruit in New York City, Alpha Centauri would be another grapefruit sitting in Los Angeles. The scale alone makes intuition fail. But distance is only half the problem. The other half is speed, and speed in space is governed by a constraint so fundamental that it has turned every interstellar mission concept into a study in impossible trade-offs. By the end of this video, you will see exactly why the rocket equation, energy density, and the physics of deceleration have kept the nearest planetary system locked behind a barrier no current technology can cross. Voyager 1 launched in 1977 and is now the most distant human-made object, traveling at 38,000 miles per hour. That sounds fast until you point it at Alpha Centauri. At that speed, the probe would arrive in roughly 75,000 years. Voyager is not aimed at Alpha Centauri, but even if it were, the trip would span more than 3 times the entire length of recorded human history. The Parker Solar Probe, designed to dive close to the Sun and currently the fastest spacecraft ever built, reaches peak velocities around 430,000 miles per hour during its closest approach. Even at that blistering speed, it would still take 7,000 years to cover the distance. These are not estimates with wiggle room. They are the result of dividing distance by velocity, and the numbers make it clear that chemical propulsion, no matter how optimized, is not a solution for interstellar travel. Chemical rockets burn fuel to produce thrust. The problem is not that the fuel lacks power. The problem is that to go faster, you need more fuel. And more fuel makes the rocket heavier, which means you need even more fuel to move the weight of the fuel itself. This feedback loop is called the rocket equation, and it becomes vicious at interstellar scale. To accelerate a spacecraft to even a small fraction of light speed using chemical rockets would require more fuel than the combined mass of every star in the Milky Way galaxy. That is not an exaggeration for effect. It is the exponential cost written into the physics. The rocket equation does not care about ambition. It enforces a hard ceiling on what chemical energy density can achieve, and that ceiling sits far below what interstellar travel demands. So, engineers look to nuclear propulsion. In the 1960s, a concept called Project Orion proposed using nuclear bombs as fuel. The idea was to detonate a series of atomic explosions behind a massive spacecraft, each blast pushing the ship forward through a shock plate. The design was technically plausible and could theoretically accelerate a large crewed vessel to a few percent of light speed. But it required thousands of nuclear warheads, raised enormous political and environmental concerns, and still left the ship crawling relative to the distance. Even at 3% of light speed, the journey to Alpha Centauri would take nearly 150 years. That span exceeds the operational lifetime of any known material or system, and it assumes perfect reliability across more than a century of exposure to cosmic radiation, micrometeorite impacts, and thermal cycling in the void. Ion drives offer another path. These engines use electric fields to accelerate charged particles, producing very small amounts of thrust over very long periods. They are efficient in terms of fuel mass, but their thrust is so weak that accelerating to interstellar speeds would take decades of continuous operation, and the power requirements grow enormous. Solar panels fail in deep space because sunlight becomes too dim. Nuclear batteries decay over time. The energy budget for an ion-driven interstellar probe quickly becomes a design trap with no clean exit. Then there is Breakthrough Starshot, a concept that tries to bypass the rocket equation entirely. Instead of carrying fuel, the probe would carry a lightweight reflective sail. A massive ground-based laser array would fire a concentrated beam at the sail, pushing it to 20% of light speed within minutes. The probe itself would be no larger than a postage stamp, a microchip with a camera and transmitter embedded in a thin, reflective membrane. The laser array would need to output roughly 100 billion watts, equivalent to the combined output of 100 nuclear power plants, all focused on a single tiny sail as it accelerates away from Earth. The engineering challenges are staggering. The sail must survive temperatures that would vaporize most materials. The beam must remain focused across millions of miles with near-perfect precision. Any wobble or drift would send the probe tumbling off course. And even if all of that works, the probe would reach Alpha Centauri in about 20 years. But at 20% of light speed, it would pass through the entire star system in just a few hours. There is no fuel left to slow down. The mission is a one-way flyby with a narrow observation window and a 4-year communication delay for every image sent back. Deceleration is the silent killer of almost every interstellar propulsion concept. Slowing down requires as much energy as speeding up. A probe moving at a significant fraction of light speed has enormous kinetic energy, and shedding that energy means either carrying a second fuel supply equal to the first, which doubles the mass and drags you back into the rocket equation, or using some external method like a magnetic sail that interacts with the interstellar medium. But the interstellar medium is so diffuse that magnetic braking at those speeds would take years and require a sail hundreds of miles wide. No current material can survive the structural loads. Without a way to decelerate, every realistic mission becomes a flyby. You spend decades crossing the void, then blink past your target in hours, hoping your instruments capture enough data in that brief window to justify the cost and risk. And there is another problem that does not appear in propulsion papers, but becomes unavoidable at relativistic speeds. Space is not empty. It contains hydrogen atoms, dust grains, and microscopic debris. At 20% of light speed, a collision with a single grain of sand releases energy equivalent to a hand grenade. There is no shielding light enough to carry on a postage stamp probe that can stop that kind of impact. Every grain becomes a potential mission killer. The faster you go, the more dangerous the environment becomes. Even a hydrogen atom, normally harmless, hits with enough force to damage sensitive electronics. The radiation environment also intensifies. Cosmic rays are high-energy particles that stream through space constantly. A slow-moving probe like Voyager can be shielded with modest amounts of material. But a probe moving at a fifth of light speed experiences those same particles as a head-on collision, and the relative energy goes up dramatically. The electronics must either be hardened to withstand constant bombardment or buried under shielding that adds mass and drags performance back down. Then there is the communication lag. Alpha Centauri is 4.37 light-years away. A radio signal traveling at the speed of light takes 4.37 years to reach the system. A reply takes another 4.37 years to return. That means a round-trip message exchange takes 8.7 years minimum. If a probe detects something unexpected and sends a query to mission control, the response arrives nearly 9 years later. By then, the probe is either moved on or shut down. Interstellar missions must be fully autonomous. Every decision, every course correction, every response to malfunction or discovery must be handled by onboard systems, with no real-time input from Earth. We have never built a machine that can operate independently for decades in an environment we cannot test or simulate completely. And the energy problem does not end with propulsion. Once a probe leaves the inner solar system, sunlight becomes too weak for solar panels. Nuclear batteries, called radioisotope thermoelectric generators, provide power by converting heat from radioactive decay into electricity. But they degrade over time. The plutonium-238 used in most designs has a half-life of 87 years, meaning the power output drops steadily. A probe designed to function for 50 years must carry enough fuel and manage enough thermal load to stay operational as its power source slowly dies. Every instrument, every transmission, every bit of data processing must be budgeted against a declining energy curve. There is also a strategic paradox called the wait for better tech problem. If we launch a probe today using current propulsion, and 50 years from now we develop a faster system, the second probe could overtake the first before either reaches the target. That creates a disincentive to launch at all. Why commit resources to a slow mission when waiting might allow a faster, cheaper, better one? But waiting indefinitely means nothing ever launches. The paradox has no clean resolution. It sits in the background of every interstellar proposal, a reminder that the timeline for these missions exceeds the stability of funding, political priorities, and sometimes even the institutions that propose them. Alpha Centauri is not just a distant point of light, it is a triple star system. The two larger stars, Alpha Centauri A and B, orbit each other. The third star, Proxima Centauri, is a small red dwarf, slightly closer to us than the other two. Proxima hosts at least one planet, Proxima b, an Earth-sized world in the habitable zone, where liquid water could exist on the surface. That makes it the nearest potentially habitable planet we know of. But Proxima Centauri is a violent star. It produces powerful flares, some thousands of times stronger than anything our sun generates. These flares blast the planet with radiation and charged particles. If Proxima b ever had an atmosphere, the flares may have stripped it away over billions of years. The planet is also likely tidally locked, meaning one side always faces the star in permanent day, while the other side sits in permanent frozen night. Whether anything could survive in that environment is unknown. But the fact that a rocky planet exists in the habitable zone of the nearest star gives the mission a concrete target. It is not abstract exploration. It is the search for another world. And that makes the engineering failure feel heavier. The distance is not arbitrary. The nearest potentially habitable planet is still 25 trillion miles away. And every propulsion concept we have either takes tens of thousands of years, requires the energy output of 100 power plants, or ends in a flyby with no way to stop. If we wanted to send humans, the problems multiply. A crewed ship needs life support, radiation shielding, food, water, air recycling, medical supplies, and living space. It needs to function not for years, but for generations. Any ship slow enough to be buildable with near-term technology would require multiple generations of people to live and die on board before arrival. That introduces biological, psychological, and social uncertainties we have no way to model. We have never kept a closed ecosystem stable for a century. We have never managed a multi-generational society in isolation. We do not know if human reproduction works normally under constant low radiation exposure or in artificial gravity. A generation ship is not just engineering. It is a social experiment with no control group and no way to abort. And even if all of that succeeds, the ship arrives at a system we have observed only from a distance. We do not know if Proxima b has a magnetic field, a breathable atmosphere, stable water, or surface conditions compatible with landing. The first crewed mission would also be a blind landing with no retrieval option. So why does the closest star remain unreachable? Because the rocket equation makes chemical propulsion a dead end. Because nuclear propulsion concepts either require city-sized laser arrays or thousands of bombs. Because deceleration demands as much energy as acceleration, and we have no light enough system to do both. Because space at high speed is lethal, full of dust grains that hit like explosives and radiation that cooks electronics. Because communication lag makes real-time control impossible, and autonomy at that scale has never been demonstrated. Because energy sources decay, solar power fails in deep space, and every instrument must run on a budget that drops year by year. Because even our fastest probe, built with decades of experience and cutting-edge materials, would still need 70 centuries to arrive. The evidence does not leave room for optimism about near-term missions. Alpha Centauri is 4.37 light-years away. That makes it the closest star. But closest does not mean close. It means 25 trillion miles, a gulf so wide that every propulsion system we can build either takes longer than civilization has existed or requires power we cannot generate, or results in a flyby so fast that the destination becomes a blur. The gap between closest in astronomy and reachable in engineering is not a funding problem or a priority problem. It is a physics problem, and the physics has not changed. What this means is that interstellar travel is not a matter of iteration or optimization. It is a matter of breakthroughs we do not yet have in energy storage, propulsion physics, materials science, and autonomous systems. Until those breakthroughs arrive, Alpha Centauri will remain what it is now. Visible, mapped, tantalizing, and completely out of reach. The nearest star is still too far. That is not pessimism. That is the conclusion the numbers force. And until the numbers change, the closest planetary system in the galaxy will stay on the other side of a barrier we can see but cannot cross.